Hey everybody, and welcome to another JASP video. Here we are continuing our mini-series on the Learn Stats module right here. Now, if you're wondering where I got this Learn Stats module, well, you have to update your JASP to 0.18.1. Now, if you just have 0.18, you might want to update to this 0.1 hotfix because the introduction of the Learn Stats module is official in this 0.1 hotfix. So definitely want to update your module here. And I also want to mention that there's a previous video on the channel where I talk about some of the changes that came to 0.18, which the majority of would be found in the new data editor. So check out that video. The 0.1 hotfix here also fixed some of the issues that I had in that video. So check out the hotfix notes. I think they just made some tweaks here and there as to how the data got how the data chats with the CSV file that you are using. And so a little bit more noticeable and seamless kind of way than some of the issues. I might do another video on that, but that's not for this video here. Another thing that I noticed for this video, as we get into Learn Stats module, just there's probably going to be a chapter to skip ahead if you don't want to hear anything. But they've added this, suggest your institution join the JASP cooperative, and so we have this rotating set of universities and organizations, many of which are in Europe. So KU Leuven, Tilburg University, many of which are in the Netherlands as well, which is where most of the devs for this app are located, including the main guy, EJ Wagenmakers. I hope I said that right, EJ, if you catch this video. All right, let's jump into our next Learn Stats, not Learn Bayes. I already have stuff on that. Learn Stats. So we are going to, as you can see here, it says Learn Classical Statistics. So Learn Bayes is Learn Bayesian Statistics. Learn Classical Statistics with simple examples and supporting text. I love it. Now, if you don't know where to find the Learn Stats module, well, good news. All of the modules come pre-built into JASP. You click on the plus sign here, and you can check and uncheck all of them here. And so Learn Stats, they are all in alphabetical order, which is nice. I love it. So we've got Learn Stats and Learn Bayes right there. You check them, you uncheck them. Checking them puts them on your top bar. Unchecking them takes them off your top bar. So let's jump in. So in the first video in this series, we did normal distribution. Had some issues, but again, this is in a beta format, so there will be issues. I have a video coming out, or it should be out by the time this video comes out, which is on the binomial distribution. And in this video, we're going to talk about the central limit theorem. So let's click on that one. It's going to load up the central limit theorem. Now, one of the things to note in the 0.1 hotfix, the 0.18.1 hotfix that you can download from JASP's website now, is that the beta text in yellow at the top of the screen is gone. And so they feel a little bit more comfortable about what you see in here and all of the ways that you can talk about this stuff here. Oh, well, for some reason I can't show explanatory text, so I'm not entirely sure. Let's see what the I says. Okay, so information is still not in, but that's okay. I noticed that when we recorded the first episode, the overview of the series. All right, so let's jump into the central limit theorem module or function here for Learn Stats. Okay, so by default, we have our parent distribution right here, okay, with the mean and standard deviation set to your standard normal distribution of mean 0 and standard deviation of 1. So we have the graph shown here. It shows the mean as 0, and then it has that lovely curve with the density on the side showing you the density, okay, of the curve, right? So we've got the peak at 0.4, and then as you can see at 3 standard deviations below and above the mean, the tails start to asymptote towards 0. So those are the kinds of pieces of information that you can get here. You can also uncheck to not show the parent distribution, and it'll disappear and just show the samples that have been pulled. But I think always showing the parent distribution, if you are using this to learn, always gets you what you need, because this is the theoretical distribution for a normally distributed variable. So I would always consider this to be something that you'd want to show, and you can also resize it to make it look a little bit more dominating, right? And it will change the axes here to stretch out as well. We can also do a uniform distribution, which is going to give us a block around a mean, and our range is 1. So this is a standard uniform distribution, okay, with the mean at 0, and then the range of 1, which is generally half a half a value less than the mean and a half a value greater than the mean. But you can obviously change this range here, but that's the standard uniform distribution. And then we have a skewed distribution, which is a take on the normal distribution where you can change where the skew is for each of these parent distributions. So we will have our mean and our standard deviation. So you set your normal distribution and then you set your skew direction. So you can have the left side be the tail where it drags on into a greater sense of infinity here, right? Or we can right skew and put the tail on the positive side of our mean of 0. And then you can change the skew intensity. Now, you cannot specifically put any kind of skewness or kurtosis value in here, which I think is useful for a basic demonstration of the central limit theorem rather than any other kinds of discussion about what can happen to distributions. So we have low skew, medium skew, which will then take the skew a little bit more, right? And so we have our mean here at 0, but of course our median is somewhere less than 0. And then we can also have a high skew where you're going to have the mean pulled even more. And it's thinking. There we go. So a high skew here where the median now is probably closer to -1 than the moderate skew or medium skew, and then we have a ton of values still trailing past 3 standard deviations. And this, of course, is going to affect all of the samples that are drawn. So let's talk about these sample options. I'm going to bring it back to normally distributed, okay? And so by default, you get a number of samples, okay, until sample number 100. Okay? It looks like it shows, a good sample, but let's crack this open, okay? So number of observations per sample. By default, it's 30, and that's what these little tick marks here are. And these sample marks are where each of those means are, or each of those values are in the distribution. And then total number of samples is 100. And of course, your computer, or at least the code here, is saying, well, we're not going to generate all of these samples. This is just a learning module, okay? So, we're going to show you 7 and show you how different values can show up on histograms, but that's not necessary. Show samples, we got last, range, and all. So by default, again, it's only going to show the sample. But of course, if I do all, oh boy, let's see. It's thinking. It's got to do all of the sampling. It's gonna sample 100 times, and then it's got to generate your images, right? It's got to generate these samples, and then it's got to generate those images. So this is probably going to take a while, and I am going to hard cut when they show up. Okay, so it actually took shorter than I thought, but I'm going to start scrolling down here. Okay, ever so slowly, and you can see all of these samples. Now, the sample graphs, histograms themselves, are smaller than they were when we just did all 7. So by default, what I was saying earlier, by default, it only shows the first 7 as to not put too much drag on your computer. I think that's really important because not everyone has a fancy machine. I don't even think my 2020 iMac here is that much of a fancy machine anymore. When I bought it, it was like top of the line and everything, but now it's not so much because, of course, Apple's moving toward their own chips, not Intel chips. So, this little gal struggles a little bit, but as we keep going, right? See, look at it. It's getting, I probably won't update this. I won't change the all. We'll just keep doing it. And you can see one thing to note as we're going through this. So if you're watching this video to learn what central limit theorems are, or what the central limit theorem is, I don't know why I said are, and looking at what is happening, this is a good indication about what happens with samples, right? So again, each of these tick marks that you see are values in the count, right? So as you can see here, we've got a lot of tick marks right here just below 0, and then that means that this histogram here is somewhere around 10. Now, of course, the ticks are all kind of blending together. This one's a little bit easier to see where you have ticks kind of filling in gaps or less gaps here. So we've got more dispersed. But of course, you can see that our means are still pretty close to 0 every time we do this, right? 0.3, negative 0.38, 0.15, right? We're not, this is even the closest one that I've seen is 0.01 here. And you can see that like none of them are going that much higher than, I don't know, 0.5, maybe even less than that. And hey, we made it to NR sample, NR or shorthand for number. I think this NR shorthand is more of a European English shorthand. So if you are in another part of the world that learned English somewhere else or from, if you're in Latin America and you learned English through American English, then NR dot is probably not a common abbreviation. It would be NO dot. But I can see the confusion about that being an abbreviation from Europeans because there's a lot of languages where no is no. I mean, it's that in English too. So I don't know why. I don't know why we do that. Anyways. Showing samples. So this is checked by default, right? So I think that's a good thing to leave on by default. You can see what the samples are doing, right? But you can always uncheck that. And then show rug marks. That's what these little things are, these little rug marks here. I am not going to uncheck that because I have it set to 100 samples. And so it's probably going to have to redraw everything, maybe even resample everything, because I'm sure the rug marks are a part of the sampling process of the code. And unfortunately, the explanatory text isn't available in this. Maybe this is coming in a future update. And then you can set a seed value of 1. Again, this would, you know what, I'm going to have to save the first. Yeah, let's just do the first 7. Let's just redraw it. As I go back up here, it's going to redraw it. There we go. So if we set the seed let's set it to 10 and then click off of that, this will, so if you want, so it's going to do some calculations right here. And so it's going to, I'm not entirely sure what the seed 1 does. Yeah, let's go back to 1 and see what happens to these. Click off of it. Yeah, I think it just changes the kind of sampling that it does. We'll just leave that for now. I'm not entirely sure what the set seed does. All right, so that's sample options. That's the samples here. Now let's take a look at the yellow distribution, which is the sampling distribution. So this is the sampling distribution of the mean of our 100 samples. Okay, so this distribution is the combination of all of my means that were calculated here, which is why these mean numbers here are represented in gold, because now I have 100 rug marks here of means. Okay, so these are my rug marks for the sample itself. These are the values in the distribution. And these are my rug marks for the means. So we take this mean of 0.06 and we plug that in right here, right? This is one of the values down here. And so then we collect all of those and we draw in our histogram, and then we put the probability density curve on top of that. And we get the mean for that probability density curve, and it is 0.02, which is only 2/100ths or 200ths away from our parent distribution mean of 0. So I think we did pretty good. And with 100 tick marks, you can see that this is a fairly normal distribution, maybe a little bit closer to the low right skew that I showed in an earlier part of the video, but relatively normal. And that's because the central limit theorem holds that your sample means are going to be approximately your normal distributed mean parameter, which here in this case is 0, when you have a sufficient number of observations. So this becomes approximately normal when we have a sufficient number of observations. Now I can change this total sample to 1,000 and watch what happens to this sampling distribution. It's going to change there. The little icon tells you. And then, of course, here we go. We have our mean value of 0. Look at that. So I'm glad I had the sample set to first 7. So I did to first 8 because, although I guess, so they would have this be lined up with that. I guess that makes sense. And so you can see all of these rug marks here are 1,000 observations of means from this sample of means. So nothing really changed in this sample here, sample number 7. It just had to calculate a bunch of, 900 more samples. So we still have 0.06, and that one still goes down here and forms this histogram bar. And of course, here we have our normal distribution down the side, which I think is pretty cool. Now, the options here, of course, are show sampling distribution, which is the histogram, the orange histogram, superimpose normal distribution, that's the black line here, and then show rug marks, which is down here at the bottom. Now, plot options, you can do a colorblind palette. So these are palettes that have been brought over in R. So R has a different set of color palettes. So we've got colorblind, we've got colorblind alt, which is just going to change the images here, which looks like it changes the plot over here, which is that one. Nothing else really changed. Maybe this one got a little bit darker orange, but the sample plots didn't change. We've got Viridis, and these color palettes can be found in lots and lots of different places. So Viridis is not my favorite. I do not like Viridis because it makes everything like oversaturated in my opinion, okay? But there you go. This changed to purple. It looks black from a distance, but it definitely is purple. We've got ggplot 2, which, is fine. It's a darker orange here, which doesn't really change this mean. And it changed this to pink. I am not sure why it does all of that. Or you can grayscale it. Of course, grayscaling takes away a lot of information, of course, but it helps with all kinds of printing. Now, I will say that if you were using this for a teaching demo, I would leave it as colorblind for all different types of folks who might be looking at this. There are no confusing reds and greens. So yes, green is in here, of course, and that makes an issue for red-green colorblind people. But here's the point that colorblind color palette makes is that there are either greens or there are either reds, and never the twain shall meet in a colorblind palette. So you can differentiate colors. So even though these plots are green, the sample and the parent distribution, and a colorblind person might not really distinguish that as green, it is at least not being confused with a red. And so they'll be able to spot the orange here and then this kind of orangey yellow. And there you go. And then you can do different types of bin width. Bin width here allows you to pull the histograms a little bit differently. So Scott changes not much. It's a little bit thinner for the sampling distribution. I'm curious if many of the plot options are actually just applied to the color palettes. Looks like it's applied to everything, but I'm curious if the bin width really changes only the sample distribution. The Doan or Donny, that's a little bit thicker. Oh, no, it actually did change these. The Friedman-Diaconis method. Let's see what it does. Okay, a little bit thinner, so very similar to Scott. And then you can do manual where you can change the number of bins. And so if by default it's 30, and so you can see that all of the rug marks actually do lead to thinner bins, thinner bars too, or bins, bars. It's there by default. It's Sturgis, and I think that's fine. You can see here. I think Sturgis kind of matches with this a little bit better. Okay, now you can do all of this again with uniform. Watch it go through. I'm just going to quickly go through these, and you can see that with 1,000 samples, our bin width is and our bin width here, and we are within 1 standard deviation of our normal distribution, and our mean is 0 as we have anticipated. And then we can also do skewed, which will give us the similar things, but in the end, even skewed distributions are going to look a little bit normal in the end. Now, I'm saying in the end, they're still going to go around a mean of 0. And you can see that with only 2 decimal places displayed, it is actually a negative number. So there is a negative value either in the thousandths or 100,000ths place of this value. So you can see that with a skew, what happens with the sampling. So I think that's pretty cool. And that's going to do it for this demonstration and overview of the central limit theorem function of the Learn Stats module. Thanks so much for watching this video. If you have any comments, suggestions, other feedback, or questions, please leave those in the comments down below. I'll see you in the next one. Bye.